let's fix the integration constant a. So here is our condition. And the problem, as we discussed it earlier when we were solving this differential equation, that when x is equal to 0 and we choose this C2 contour, their solution is in fact divergent. Indeed, because you clearly see that when you put x is equal to 0, the exponential factor becomes 1, and you integrate from minus I to minus infinity, and the integral is logarithmically divergent. And indeed, we put it, so we said that, so actually, this gives us the reason to assume that the leading behavior would be logarithmic, but well, right now it's the logarithm of infinity, but the upper limit of integration should be changed from minus infinity to minus 1 over x, and the answer would be like this. This is a leading logarithmic behavior. But what we are interested right now is just to get the answer, not with logarithmic accuracy, but to catch the constant which is present here. So let's do this, because this is just an interesting exercise by itself. So how would we do this? So instead of just putting x to be equal to 0, we consider it, of course, to be small but finite number, and address again our integral. So as we discussed before, the problem comes from this 1 over t behavior of their g function, right, of this additional pre-exponential function. If, for example, this function would decay much faster, like 1 over t squared, for example, or even 1 over t to the 3/2, then we would get the finite answer at x is equal to 0. So what we should always try to do when we try to find out that kind of asymptotics, we should try to simplify this function. For example, 1 over t squared, square root of t squared plus 1. For large t, it behaves like 1 over t. So let's make the following trick, which almost always works. So we subtract this simplified function 1 over t from the initial one. And now this factor actually converges much faster than 1 over t. Basically, it converges like 1 over t cubed, I think, right? So this expression now is well defined when x tends to 0. And so we subtracted it. And then, of course, we need to add the same term. And this now integral has inherited the same singularity. So it's log divergent when x tends to 0. Right, but it's much simpler than the previous one, and it's much easier to deal with. So this one, since we're interested in the behavior at small x, here we could safely put x to be equal to 0, and the whole exponential function becomes 1. And you basically perform this trivial integration. Well, I'm not going to do this right now. It's just trivial, and the answer is the logarithm of 2. Here, well, what you can do here? Well, you can simplify slightly things by making an appropriate change of variables. For example, you can change xt to be equal to, since, well, t is negative, so you can change it to like minus s, for example. And then the integral is changed from, is taken from now from ix to plus infinity. And here you have e to minus s ds over s. Well, and this integral is easily estimated by simple integration by parts. So what you do, sorry, I dropped a here. But anyway, so what you do, you just represent it 1 over s, the derivative of the log of s. And here we go. So it's, sorry, I put it, continue here. It's logarithm of s e to minus s from ix to plus infinity, minus a, the integral from ix to plus infinity, and you have to differentiate e to minus s, which gives you just the same e to minus s, but the sign changes. E to minus s, logarithm of s ds. Now, this expression is well defined when x tends to 0. So now you can safely change the lower limit to 0. So I hope you recognize what this is. This is simply the Euler constant which we encountered during one of our previous lectures. So it's the constant which we called minus gamma, right? It's a logarithmic derivative of gamma function at 1. This, however, okay, now you see that this term is crucial for us. It is this term which defines our logarithmic behavior, right? The lower limit is just the logarithm of ix. So now you have the full answer for the function, for the behavior of the function at small x. So here are constants which we were fighting for: logarithm of 2 minus Euler constant gamma. And here we have minus logarithm of ix. So what is logarithm of I? Well, that's a good question. So in order to find the value of logarithm of I self-consistently, you actually need to draw a branch card to define this logarithm in a single valued way. So, okay, let's do this. Just small picture. Okay, let's draw a branch card, for example, in the positive direction, for example, like this. And then you compare the value of your function at plus infinity, obviously plus 0, and somewhere here above the branch card, and here at point I, right? And you see that the change of the argument is pi by 2. So you need to choose the correct value of the logarithm of I as e to I pi by 2. Okay, so now you get logarithm of e to I pi by 2 x. Right, so, and finally we get the answer. So our answer is the logarithm of 2 divided by x times e to gamma and minus I pi by 2. So the imaginary part of our u function now, as you see, is minus pi by 2 times a. So this is happened to be minus pi by 2 times a. And this should be equal to 1. So now we extract the correct value of our integration constant. It's minus 2 over pi. And finally, we get the structure, the full structure of our asymptotics and our solution for all important values of our x, for small x, large x, and with the correct integration constant. So let me write it down for you. So, and here we are. So this is our entire study of this differential equation. So defined by this contour, right? So this is our exact solution in the form of complex integral, and these are the all limiting casing which are available for asymptotic analysis. So we extracted the correct behavior, logarithmic behavior of our function at small x, and then these are our asymptotics at large x. So here we see that generally for large positive x and for large negative x, there is a similar part of the asymptotics, which is basically one is the analytic continuation of the another one, right? But then the additional term appears due to the strong deformation of the contour when we switch to the left-hand side of our in the complex plane of our variable x, right? In fact, the appearance of this solution, well, as you see, those solutions remind us slightly of incident or reflected waves in one-dimensional quantum mechanics. For example, this one looks certainly like, for example, a wave moving from the right, from the left to the right, like an incident wave. And this certainly reminds us the reflected wave. So it's precisely that kind of phenomenon which leads to the scattering events in quantum mechanics. Now you can see that just, I would say, beautiful beautiful connection between the deformation of abstract contours in a complex plane and some physical interpretation of a problem, of a mathematical problem. So I think that's it for today. Thank you.